The enormity of space is difficult for humans to fully comprehend. We are comfortable in our own cosmic neighborhood, the solar system, used to familiar faces like Jupiter, Mars, and, of course, Earth. But out there, over 18 billion kilometers away from the Sun and beyond the heliopause, is the cold oblivion of interstellar space. The two Voyager probes are the only man-made objects ever to cross this threshold. Their passage decades ago marked a symbolic boundary, yet the probes themselves are merely drifting, their power fading as they exit our magnetic and gravitational comfort zone. To receive a visit from the outside, however, is a far rarer and scientifically richer event. Until recently, only two known objects had ever made the opposite journey, passing from interstellar space into our solar system. These were the famous Oumuamua in 2017 and Borisov in 2019. Their visits brought with them the thrill, and perhaps even fear, of being visited by something from the depths of space that humans cannot hope to reach in our lifetimes. The sheer scarcity of these events underscored the importance of each sighting. In the 6 years since those visits, we've been enjoying some respite. But a recent observation has forced us to sit up and pay attention once more. Join us as we explore all there is to know about NASA's latest observations of Comet 3I Atlas, the third interstellar object ever observed. It will make its closest approach to our Sun before the year is out. 3I Atlas has had a few different names in the short time we've been aware of it, but recent revelations about its origin and trajectory have turned this otherwise indistinguishable space rock into something worth taking note of. On the 1st of July this year, the NASA-funded ATLAS, Asteroid Terrestrial Impact Last Alert System, survey telescope was performing its usual task of scanning the skies for moving objects. The ATLAS project, with its wide-field telescopes, is an exceptional tool for exactly this purpose, rapidly scanning vast swathes of the sky. Its power lies not in deep, detailed observation, but in its last alert function, ensuring that fast-moving, potentially dangerous or scientifically unique objects are flagged immediately. The ATLAS project consists of 4 telescopes across Chile, South Africa, and Hawaii. These telescopes each take around 800 images every night. At the time of writing, they have registered 1,112 near-Earth objects that will pass within 1.3 astronomical units of our planet at perihelion. On this particular night, the telescope in Rio Hurtado, Chile, reported some newsworthy observations. The ATLAS telescopes are unique for their ability to survey the galactic plane, the bright disc-shaped region of our galaxy where most of its mass lies. Its ability to survey the bright galactic plane is a game-changer, as it allows for the discovery of objects that might otherwise be masked by the sheer density of stars in that region. Other surveys, like Pan-STARRS and the Catalina Sky Survey, are often too sensitive to photograph this area without overexposure, so they tend to avoid it altogether. From the direction of the Sagittarius constellation, the ATLAS telescope took 4 30-second survey images and found an object making a beeline toward our solar system. The object was initially named A11PL3Z and quickly caught the attention of the Minor Planet Center, MPC, in Cambridge, Massachusetts. As the designated authority in charge of labeling and tracking minor bodies in the solar system, the MPC quickly put out an electronic circular detailing all of its previous observations and providing information about its trajectory. The Minor Planet Center's quick action in gathering pre-discovery data was crucial. These are observations made by other facilities before the object's interstellar nature was confirmed. Like finding a breadcrumb trail, astronomers realized the object was no stranger. It turned out that the Zwicky Transient Facility in California and the other Atlas telescopes had all made pre-discovery observations dating back as far as June 14th. With all of this data, the MPC deduced that the object had a hyperbolic and highly eccentric orbit, so much so that it had originated from interstellar space. The combined data was the key, painting a clear picture of an extreme, highly eccentric orbit. This realization earned the object the name 3I Atlas, as it is the third interstellar object to infiltrate our solar system. The MPC initially could not be certain whether this object was an asteroid or a comet. However, the combined data revealed that it had a coma, a diffused halo of dust and gas, produced when ice is exposed to solar radiation and sublimits. This feature is far more typical of comets, which gave the object yet another name, C-2025-1. The MPC has called for additional observations of this comet to help constrain its trajectory, so we can expect a flurry of new data in the upcoming months. Astronomers are naturally very excited, noting that working on the two previous interstellar visitors were transformational opportunities for science. It's likely this visitor will encourage the same. What do we already know about this latest interstellar visitor? And what do scientists hope it can teach us in the near future? Firstly, don't worry. This comet poses no threat to Earth. At its closest approach to our planet, it will still be around 1.6 astronomical units away. That's over 600 times farther than the Moon is from Earth. Since we're able to watch from a safe distance, what kind of journey will this comet take? 3I Atlas has a highly eccentric orbit, currently measuring at an E value of around 6. For reference, an eccentricity of 0 represents a perfect circle. Anything above 1 is great enough for an object to escape the gravitational pull of the body it is orbiting and move more freely through space. For an object to achieve an eccentricity of 6, its velocity must significantly exceed the solar system's escape velocity, confirming that it is not merely a long-period solar system comet, but a truly foreign body, forever unbound by the sun's gravity. With an eccentricity of 6, this comet has one of the most extreme hyperbolic orbits yet measured, which may explain how it is able to travel so far through space to reach us. What's more surprising is the speed with which this comet is traveling. Its current incoming velocity is a rapid 58 kilometers per second. That's like running the length of 580 football pitches every second. This breakneck speed makes 3I Atlas the fastest traveling interstellar comet we have ever seen. Oumuamua and Borisov had velocities of just 26 and 32 kilometers respectively, resulting from their differently shaped orbits. With such a rapid approach, astronomers were keen to work out exactly where 3I Atlas was headed. The current orbit is heliocentric, or centered around the Sun, meaning it is possible to infer its incoming trajectory before it reaches us. On its closest approach to the Sun on October 30th, the comet will be at a distance of 1.4 astronomical units, placing it just inside the orbit of Mars. In this graph of the comet's orbit, you can see the asymptotic shape of its approach as it veers past Mars and shoots back out into space. As the graph shows, 3I Atlas will not pass as close to the Sun as the famous Oumuamua did in 2017, and will follow a trajectory more similar to Borisov's. Once the interstellar nature of this comet was clear, astronomers employed globally distributed telescopes for a better understanding. Observatories are purpose-built to observe transient astronomical events, including comet outbursts and changes in brightness. Using two 0.36-meter LCO telescopes based in Hawaii, astronomers scheduled a 1-hour observation sequence for 3I Atlas. Their goal was to identify a light curve for the comet and see whether it exhibited any rotational variability. Rotational variability is any variation in brightness caused by the comet spinning on its rotational axis. This can be due to an irregular shape reflecting light differently, or active regions appearing brighter when facing Earth. By monitoring these brightness changes over time, astronomers can identify repeating patterns that show when the comet has completed one cycle of rotation. The significance of the 29-hour rotation period is that it provides a baseline for understanding the comet's overall structure and integrity. Rotational variability is key. Oumuamua, for instance, exhibited significant and rapid changes in brightness as it tumbled, which helped scientists constrain its highly elongated shape. Using the LCO telescopes, astronomers identified a rotation period of around 29 hours. Like much of the information about 3I Atlas, further observations are needed to constrain this. In a surprise to astronomers, 3I Atlas had a much flatter light curve than Oumuamua, exhibiting only 0.2 magnitude of brightness variation throughout the 29-hour period. The fact that it shows a much flatter light curve suggests a more symmetrical or spherical shape than its famous predecessor. It's spinning, yes, but it doesn't appear to be tumbling or have a dramatically irregular silhouette, setting it further apart from Oumuamua. Despite this minimal variation in brightness, 3I Atlas is remarkably bright. In fact, it's the brightest interstellar object we've seen yet. The comet was quite faint until the end of May this year, when it reached a magnitude of around 20. But between then and its discovery by Atlas, it promptly increased to between 17.7 and 17.8 magnitude in the Atlas O band, which records light wavelengths between 560 and 820 nanometers. The extreme brightness of 3I Atlas is equally important. Going from a faint magnitude of 20 to nearly 17.7, 17.8 in a short period indicates a rapid increase in activity. More sublimation, more coma, and more reflected sunlight. This exceptional brightness is directly linked to its immense size. Not only is the comet bright, but it is large. From assumed albedo values, the diameter of its nucleus is estimated at 10 kilometers. This makes it an order of magnitude larger than Oumuamua and even larger than Borisov, which measured between 1 to 2 kilometers in diameter. To put that in perspective, this nucleus is likely the size of a medium to large asteroid or a small mountain, dwarfing the previous visitors. This sheer size means it contains a massive reservoir of pristine interstellar material, making it an unprecedented target for compositional analysis. Further observations have also revealed that 3I Atlas shows faint levels of activity. The comet has a marginal coma, the fuzzy, glowing halo of dust and gas produced when cometary ice sublimates upon exposure to the sun. You can make it out in the center of this image as a diffused circle around the nucleus. The image is tracking the moving comet, which is why the surrounding stars appear blurred. As well as a coma, 3I Atlas has a tail. The MPC reported a tail spanning 3 arcsecons across the sky at an angle of around 280 degrees. This is pretty short, so the tail is often lost amongst the coma in images of the comet. As with many modern scientific discoveries, advances in technology and communication mean that people from around the world can get in on the excitement. This is exactly what is happening for 3I Atlas. Amateur astronomers and experts alike are contributing their own observations, so our state of knowledge is constantly being updated. For example, the Astronomers Telegram is a forum for space enthusiasts to post their findings and is being updated daily with new revelations. Observations have helped to constrain the tail measurements for 3I Atlas, reporting that it extends across more than 25,000 kilometers. The tail measurements are also continuously being refined. This dynamic, Collaborative refinement of data is a hallmark of modern science, where the global community tracks an event in near real time, rapidly improving the initial estimates of its physical characteristics. From these posts, we can see some really exciting images of our new visitor. Just look at these. We've covered brightness, rotation, and activity on the comet. But what about its surface? In this respect, 3I Atlas is similar to its predecessors. Just like Oumuamua and Borisov, 3I Atlas is significantly redder than the Sun and slightly redder than D-type asteroids like those from the outer asteroid belt. This reddish hue, similar to D-type asteroids and the previous interstellar visitors, is likely due to the radiation processing of organic materials on its surface, a cosmic suntan acquired during millennia of travel through space. Since the comet is active, some of this reflected light must be coming from its coma. The same was observed for Borisov, where the reflectance of the coma was drowning out the signal from the nucleus itself. We should be able to confirm this as the comet gets closer to us and new measurements can be made. For example, in 2020, astronomers found that Borisov was producing dust at a rate of 50 kilonewtons, which helped to explain the obscured nuclear signal. Finally, the discovery of 3I Atlas has allowed astronomers to make a new estimate for the density of interstellar objects. In a paper published shortly after the comet's discovery, scientists inferred a density of just 0.001 interstellar objects per cubic astronomical unit of space. That's far smaller than the previous estimates made when Oumuamua and Borisov were discovered. This density value is based on the fact that Atlas has been scanning our skies for the past 3 years and has only found one interstellar object so far. Of course, the density is liable to change and depends on many other factors. It could be that Atlas has let some objects smaller than 3I Atlas pass by undetected, or that there is a particular signal emitted by these objects that it fails to detect. We're not really sure, but estimates like these are useful to us, and we should try to update them whenever we're given the opportunity. So, we've explored the information we've gathered about this comet so far. But, as we've seen, science is anything but stagnant, especially when there is a brand new object to study. What are we hoping to learn from this comet in the near future? And how can we learn from our previous interstellar visitors? Luckily for astronomers studying 3I Atlas, there are 2 fairly recent case studies to draw from: Borisov and Oumuamua. We've already discussed some of the similarities and differences, but how can these comparisons be explained, and what do they tell us about the origins of these visitors? One of the major differences is that 3I Atlas appears to be less active than Borisov was. 2I Borisov displayed significant cometary activity. Its dust coma increased in size by around 1% per day, indicating it had been active for about 100 days prior to its first observations. It also had a longer tail, spanning 140,000 kilometers into space. It could be that 3I Atlas hasn't been exposed to the sun enough to begin water ice sublimation, which would raise activity levels. However, Borisov entered a period of strong activity when it was still 4.5 astronomical units away from the sun, and 3I Atlas is already much closer than that, so this looks unlikely. The current low activity of 3I Atlas, especially compared to where Borisov was at a similar solar distance, suggests it might be composed of less volatile ices, or that its surface is heavily crusted. Oumuamua didn't exhibit high activity levels either. It was a dense rocky body with no ice to sublimate in the glare of the sun, and it had no coma or tail. Astronomers are still trying to explain this lack of activity with recent hypotheses, suggesting it may have been outgassing volatiles with a low level of dust production that wasn't picked up in observations. But since 3I Atlas does have a coma, This explanation isn't a one-size-fits-all for all interstellar objects. With such differing compositions and activity levels, what does this tell us about the origins of interstellar objects? The differences in activity levels, from Borisov's pronounced coma and tail to Oumuamua's near-total inactivity, are central to understanding where these objects form. This remains a major subject of scientific exploration. The famous oblong shape of Oumuamua generated buzz, with theories emerging that it may be a primordial object shaped by tidal forces, a fragment of a planet, or the aggregation of several smaller objects. Borisov also caused speculation. Its composition was different from those typically seen in solar system comets. It had a higher abundance of hypervolatile carbon monoxide relative to water, suggesting that it may have formed in a carbon-rich environment. In line with this observation, it was suggested that Borisov formed in a red dwarf star system with cooler average temperatures, cool enough for carbon monoxide to condense and be incorporated into the comet. The speculation surrounding Borisov's formation in a carbon-rich red dwarf star system highlights the potential scientific windfall of 3I's Atlas. The chance to perform such a compositional analysis on an object this large and active is a true opportunity. Each interstellar visitor acts as a time capsule, carrying with it the raw, untainted material from its distant home star system, offering us a glimpse into the diverse chemistry of exoplanetary formation. At the moment, it's still too soon to say what we will be able to infer about 3I Atlas's origins. However, it is active like Borisov, and as it starts to be heated by our sun, perhaps we will detect similar levels of carbon monoxide, hinting at a shared interstellar origin. If it shows a chemical signature with a high carbon monoxide to water ratio, a hypervolatile composition, it would strongly suggest a similar origin outside of a solar-type stellar nursery. Speculation aside, it is clear that 3I Atlas is a unique interstellar visitor worthy of our close attention. Whether comparable to Borisov or Oumuamua, 3I Atlas has characteristics that place it in a different class of object altogether. As a result, we can view this comet as an exciting opportunity for new discoveries and eagerly anticipate the scientific insights it may reveal. After all, the estimated density for interstellar objects is low, so who knows how long we may have to wait to be visited again. Now that we've learned a bit about 3I Atlas, it's over to you. You can keep an eye out for this comet using ground-based telescopes from around September until it disappears behind the sun. After perihelion, on October 30th, the comet will re-emerge from behind the sun in early December, ready for another round of viewing from Earth. If you don't have a telescope, don't worry. You can still track the comet's position in space using tools like the JPL Horizons website. This comet is an unprecedented opportunity, a massive, bright, and fast visitor, giving us a front-row seat to the universe's diversity. It has come an awfully long way, beating the odds to reach us, and it is sure to have plenty of cosmic secrets to spill. Want to follow the latest updates on 3I Atlas and other interstellar mysteries? Subscribe to Stellify Science for more deep dive videos on the most exciting discoveries in astronomy. Hit the notification bell so you don't miss our next cosmic exploration. We'll see you next time.